Okay, so welcome so much for joining today for the Grass and Robotics talk series. My name is Michael Posak. So actually, no, my name is Jeff. I'll be the faculty host for this talk. Mike was generous enough to let me to introduce Jitendra today. A quick reminder, previous recorded talks can be found on YouTube channel and the website. If you're on a Zoom, please submit your questions during the Q&A using the Q&A button at the bottom of your screen, and those questions will be answered at the end of the talk. If you're here in person, you have an opportunity to talk to, during the talk to ask questions. And there are two panelists today, student panelists, Brian and Aurora, who will be managing the questions. So with that logistic out of the way, it's a great, really fun for me to introduce my own advisor. This is actually the first time I introduced Jitendra at Penn, so it's a distinct pleasure. I'm student number 8 of Jitendra, Malik. Yesterday, actually, I was just looking at mathematical genealogy to check the whole list of students. In fact, many of us are still very good friends, which is a testimony to all the hard work and suffering we endured together. You don't really become friends unless you are really working hard together. So there are 40 of us today that Jitendra had trained. And impressively enough, I counted there's actually over 20 of us are working academic, have been in the top schools. And consider only the 20 top 5 schools, but Jitendra is doing very well. In fact, some of the students are here, and some of the postdoc he trained, CJ Taylor is here. Jitendra has a long link to Grass Lab. He has collaborated with Ruzina and worked with Yana Kosaka, with students here who was a postdoc with Jitendra, and many influential works that came out of his students and postdoc. And I was just checking today, John Barron was not on the list. But John Barron, if you people don't know, was the person who are behind the Google Pixel night mode. So if you use Google Pixel, every time do a night mode, you know, John Barron was Jitendra students. And of course, John is also known for his nerve work that everyone's very excited. And one of the Jitendra's postdoc, Bjorn Omar, is the author of Stable Diffusion that everyone's using. Of course, UNet, Tom Brax was also Jitendra's postdoc, and the list goes on. So those are the people not even on the list. So Jitendra started his work at Berkeley in 1985. And that seems to be so long ago. And the hallmark of his work is really always, in my mind, going the opposite of what everyone's doing. So in the 80s, everyone's working on symbolic logics, and Jitendra decided to do signal processing. So using the filter banks, filters to understand textures. And of course, his work with Pietro Porna at Caltech now, and unstructured diffusion, which is actually used again, many times, including in the Pixel camera, I'm sure, somewhere. In the 90s, when things are going in the graphics way, everyone is doing graphics, ray tracing. He decided to do, again, the opposite, using images as way of rendering images, pictures rather than ray tracing, and start a whole trend of image-based rendering. And the work on facade, for example, with CJ Taylor, who's unfortunately not here today, is very influential, lead to the work of matrix, special effects, and so on. And then, of course, in the object detection areas, Jitendra moved on to shape contacts, which is, again, taking the low-level vision view of how to do object detection at a high level. So I can go down the list and on. But let me come back to some of the things I learned. And Jitendra always told me that it's important to think ahead. Think about what people remember you in 5 years. And to me, when I was a PhD student, that was very hard because I only started a year or two into it. And true to his work is now highly cited. As if I just checked, 150,000 citations, 4 test of a time papers. If you get one, you're very happy. Jitendra 4, at least, maybe more. 20 paper has been cited over 1,000 times, which is a major home run. So Jitendra is also, I think, quite a community-oriented person, organized many of the conferences and steering the community in the right direction. He was also department chair at Berkeley from 2003 to 2006. I might have miscounted something wrong. That back again during the turbulent times of AI in 2016 to 2017. He's a National Academy of Engineering, a member of National Academy of Science, American Academy of Arts and Sciences. This is despite the fact Jitendra really loves to accumulate any awards, never seek out for those attentions. One of the things I remember the most, one of the students is Jitendra always coming to the office in the morning and says, I have a new idea. It happens every day. And I'm always looking forward to hear that. And so today I'm looking forward to this new idea that Jitendra is going to talk about robots and learn and adapt. So welcome to Pat.
Yeah. Thank you, Janbo, for this very warm introduction. It's really a pleasure to be here at UPenn. I think it's my third time coming here. I first came in the 90s with invited by Regina, which was, I think, associated with the Cognitive Science Institute. Then I came again when Fernando invited me as a part of a CS department talk, and this is the third time. And in terms of my connection to UPenn, right now I have a postdoc, Georgios, let me try to say it correctly, Georgios Pavlakos, who was working with Kostas before, and he's fantastic. So it's a pleasure to always have this connection. And of course, Regina has been an influence on me forever. So, I'm going to talk about robots that learn and adapt. And unlike most of my career, which has been in vision, this is actually a robotics talk. So you can judge it as a robotics talk, and let's see how the professional roboticists think about this work. But I decided, I mean, I've jumped around. I've done work in human perception. I've done work in graphics. I've done work in machine learning. But somehow I sort of, now I'm in my 60s, I feel that vision is not just for itself. Vision is, in any biological organism, is part of a control loop with action. So we have not proved that we have solved vision until we have solved vision and action together. So that's the philosophy with which I got into robotics about five or 6 years ago. And I'm going to talk about some of that work. So I'm going to, this is a walking robot that we have. This is, it's made by a company called Unitree. It's the A1 robot. And this is the robot walking. It's actually blind. Most of it, what I'm going to show you is with a blind robot and later on with walking robot. And this is some rocky area near Berkeley. This is that same robot walking down. Everything is on board. All the compute is on board. So notice how varied the terrain is, and the robot has to deal with that. More examples. So I mean, I'll talk more about how we train this robot, but the key point that I want to make here is think of the variety of terrains that you have to deal with when you're walking. And this is a blind robot, but blind humans walk. I mean, it's this basic adaptivity to variability in terrain, soft terrain, sloping, up and down is in fact, you're able to do it even blind. Okay, so here's another example. So what's the central thing to learn from these examples? So in computer vision, which essentially has become a form of pattern recognition, the key thing which we have realized is that generalization is important, and generalization over appearance, pose, and so on and so forth. And that now what happens when we think about robotics and action? So this the area of psychology and neuroscience we want to connect to is motor control. And there, the key thing to note is first we need robustness. I mean, that is central to control. The concept of control is about robustness to disturbance. But also I would use the term adaptivity, and I want to use it in a different way than robustness. And adaptivity here is obviously varying physical conditions. But this applies across the board to other tasks that we might want to do. Suppose it's a manipulation task, and I want to rotate an object. I should be able to rotate an object if it's small, if it's big, if it's light, if it's heavy, if it has a smooth surface, etc. So this is central to the enterprise. Now, if we think about, so now let's come to the root discipline. The root discipline obviously is control theory. And control theory, modern control theory starts around 1960 or something. Many of the fundamental papers are in the neighborhood of 1960. And you have this basic formulation of optimal control. And today, I mean, there is this, actually the key ideas of reinforcement learning also go back to 1960. But I think of reinforcement learning as just an optimization technique for training an optimal controller. It's just when the problem is sort of tricky and complicated that you cannot analytically work out the solution, you can work out a solution with trial and error, and that's what RL is. So that's my philosophical way of thinking about RL. It's just optimal control, a search strategy for finding optimal controllers. Okay. So viewed that way, there's nothing very complicated or fancy. It's just that. Okay, I think. And Berkeley in particular has written about this quite well. And there's a difference in notation and my notation. This is a control theory type notation. I mean, in the RL community, they will replace X by S and U by A, but it's the same thing. Okay, going back again to the control theory reference, if we think about back to the 1960s, there's a field of adaptive control. And a canonical example from that time is you're flying an airplane. Now, this airplane initially is heavy because it's got all the fuel. And then later on, halfway through the flight, most of the flight, the fuel has been burnt. So the mass is now much less. Okay. Obviously, the controller should adapt to that, right? And these ideas go back there. And in my mind, there's, I mean, at that time, it was done with a compute of that time. The state was the state was very low dimensional. And the kinds of things that I'm talking about with walking robots and so on, it's going to be much more high dimensional. But it is philosophically the same idea, the same problem, okay? And there's a question of where to put in all the variability due to the environment. You can put the variability into the X and make the state much more complicated, or you can put the variability into the A matrix, right? The dynamical model. And my preference is to factor it out and put it into the A. So philosophically, the X will remain something like joint angles of the robot, and the A will capture the variability due to the environment, the terrain, things like that. And of course, so what we realized from this way of thinking is that this A matrix can be changing quite a bit. And you need to be doing different things at different times. Okay, I'm using a linear model here just for illustration. The model will actually not be linear, but conceptually, you get the idea. It's straightforward. So basically, I have to deal with the fact that this A matrix can be changing all the time. So what do we need to do? Again, if you go back to the adaptive control literature, there are what's called direct techniques and indirect techniques. Okay. So here I'm going to talk about the technique where what you're trying to do is to somehow estimate A. Estimate A in some form, not directly, but some projection of it, if you will, and then change your control law appropriately. Okay, that's it. That's the big philosophy. And now the rest is how to implement it using the machinery of deep learning. But the essence of my talk conceptually is captured already now. Okay, so I'll get into a series of papers on first on walking and then later on manipulation. But you got the big idea already. And there we developed a technique which we call RMA, rapid motor adaptation, and this is basically this machinery for doing adaptive control using the tools of deep learning. Okay, so how are we going to do this? I'm going to take you through a series of robots that have been trained, and they will get more and more sophisticated as the talk proceeds. So the first version is walking in simulation. Okay, so reinforcement learning is very sample expensive. So since it takes lots of samples, training a robot in the real world is challenging. It's much easier to do it in simulation, which then creates the problem that what you have trained in simulation is not going to work in the real world, except that I've already told you this idea of adaptation. If you have the ability to adapt, which you need in the real world, because in different conditions you have to adapt to the different kinds of terrain. Once you have provided that ability, the ability to adapt from simulation to real is just another adaptation. So it's no big deal because you need adaptation within the real world. So simulation to real is just one more adaptation. The same machinery will do the job. Okay, a philosophical point that I want to make for people who are into walking and locomotion is that we decided upfront that there will be no pre-programmed gates. And this is, of course, a very classic technique because, I mean, biomechanics for quite some time has been based on observing animals, and it's not just horses and dogs, but also, you know, snails and fish, and a very central idea there is that you train a CPG, and then gates can be determined by some kind of periodic control of the movement of the legs. It's a very natural thing. And it's a very simple circuit, and it's found in very simple animals. However, if you look at how human babies walk and human babies learn to walk, there's someone called Karen Adolph at NYU who's studied this, and it turns out they don't start with gates. They basically just hesitate. It's a much more of a learning approach. So the architecture for very simple animals and for like humans varies quite a bit. So humans basically learn to take little steps, which could be front, back, side, etc. There's a lot of learning and so forth. And smooth gaits come much later. It's not in the beginning, which is different from for some simple animals. They're born and they can swim right away, or they can walk right away. So anyway, in our approach, no gaits are pre-programmed. This turned out to be advantageous in some ways. So what do we do? So if we are using the machinery of reinforcement learning, which is basically a fancy way of saying trial and error, what you're going to do is you are in a physics simulator. You're going to train a policy. So you're going to try to take various actions, and then you give, there's a reward based on sort of how much you want to minimize the energy consumed. You want to fall as little as possible, things like that, fairly standard. And here X refers to the state and A refers to the action that you took in the previous time. The state here is all the joint angles of the robot. Okay. Joint angles and velocities, right? Okay, and what's important here is that the environment, we are looking ahead. We need to have a variable environment. So what you do is that in simulation, you must vary the conditions a lot. How do you vary the conditions a lot? You vary the conditions by varying the mass of the robot, center mass, friction, terrain height, things like that. So in simulation, actually, we have this terrain which is fractal. And fractal is nice because mathematically, you're going to get a lot of the variability of small heights, large heights, etc. And if a robot can walk in fractal terrain, that captures different kinds of terrains, and we vary these other parameters. So the first trick here is that you don't try to have exactly the same policy for all conditions. Okay, we need to be adaptive. And different policies, so there's a policy for walking on slippery ground versus not slippery ground, right? Or the kind of slope, etc., etc. So you need to do different things and different kinds of actions in different conditions. And that is essentially captured through this argument to the policy called Z sub t. So for a learning neural network person, you should think of it as a latent variable. But as a computer scientist, just think of this, that you have a function, but you add an extra argument to the function. And that is a way to create a different function for different conditions. Okay. There's an idea which has Karen Liu's group who works in graphics and robotics. I think a few years ago, they came up with this idea in the context of sort of graphic simulation, but it's a very nice idea. But just add an extra argument to the policy. And now this argument is a way of encoding all these variable parameters like the mass, friction, etc., etc. So when you are training in a simulator, you know all these things. So it's easy. You have this, and you train this policy and this environmental factor encoder end to end. Okay, straightforward. Okay, we call this this Z extrinsics. So this is a central idea here, because basically the way you are going to get adaptation to different environments is by varying the actions, which you vary because you have different Z's. And at training time, you have access to the Z because you know all the ground truth parameters of friction, center mass, etc. Okay, reward function minimizes work and ground impact. Okay, straightforward. And now you do this and you'd do 1 billion trials or 10 million trials, and then your robot is walking. But now we want to have this robot walk in the real world. And when you want the robot to walk in the real world, the problem is you do not know the Z. Okay, so the Z in simulation is known because in simulation you know all the parameters of the robot. In the real world, you don't know it. So what should we do? And this is where this rapid motor adaptation idea comes in. So we no longer have access to these ground truth parameters, and these Z's are unknown. So that's the problem. So now we are stuck. We don't know. We don't have one of the arguments to the policy, which corresponds to the environmental conditions. So what do we do? So now let's think of the following intuition. So the intuition is, one example of different environmental condition is walking on a hard surface versus walking in sand, right? And imagine that I'm blind. I'm walking on sand and I'm walking on this ground. Can I judge the difference between the two situations? I can, because I will command a certain set of actions. I mean, my controller in my head commands a certain movement of my joints and so forth. Now, the consequence of that in the real world varies depending on the set conditions. So if I'm walking in sand, I put my foot down and then I pull it up and I apply the same force. Well, my foot doesn't come out as quickly. Suppose I'm in some sticky terrain, it's going to get stuck. If I'm on hard ground, it will come out easily. So, and I am monitoring my internal state. So it's very, very important to consider proprioception. We are always, I used to be a vision chauvinist. I used to regard vision as the most important sense. This is false, actually. Proprioception is the most important sense, and vision comes after that. Yeah. Both. Yeah, I have access to proprioception and the efference copy. Okay, because I have access to the action that I commanded. The two together form the pair. Because the efference copy tells me what I commanded, and proprioception tells me what happened. And if there is an internal model, then you know that, oh, okay, there's a discrepancy, and that corresponds to the state of the environment. And that in the state of the environment here is Z. So basically, the idea is that you have the past sequence of states which you capture through proprioception, past sequence of actions which you know because you commanded them. And through this goes into this adaptation module, whose job it is to estimate the Z. And if it estimates the Z correctly, then the policy will run. Yeah. Joint angles and velocities and some a couple of parameters of the pose. Yeah. So that's the adaptation module, which has to do this job. And of course, this module is another neural network. And now the question is, so this is theoretically how it could be done. And now the problem is, how do we train this adaptation module? And the nice thing is that this adaptation module can itself be trained. So there is the actual controller that you train, and then there is this adaptation module, which is like an estimator for the state. So again, if you think back to your ideas with Kalman filtering and control theory, right? There is the idea of an observer, right? There, the observer is trying to estimate the state. Here, this observer is trying to estimate the Z, which is estimating some aspect of the environment. I mean, there is a formulation I could have had here where I could have added the Z to the state, but I prefer to keep them separate because they have different rates at which they change. The state is changing very dynamically and fast, whereas the Z, which is the environmental condition, changes relatively slowly, right? Because the state is changing every, I have to run it at 100 hertz or whatever, right? Whereas this, I'm going to run it like 10 hertz. So what you can do is you can train this adaptation module in simulation, because in simulation, you have the ground truth Z, because you have the ground truth variables. So it's actually a very easy learning problem because it's a supervised learning problem. So the Z's are given by the top part, and then you use the state history to estimate them. And so this, you can train this adaptation module also in simulation. And bingo, now at test time, you throw away all of the stuff which you couldn't have at test time. And you have this adaptation module, which is like this observer of the Z. And then you have the base policy, which is the one which is actually determining the commanded joint angles. Then there is a even lower level controller. So it's like 3 levels are going on. There is the adaptation module, which is estimating the Z, which is like an observer. There is the base policy, which is saying desired joint angles. And then you feed it to a low-level PID controller, which comes with the robot manufacturer supplies something. Yeah. Yeah. So the base policy, when it was being trained, it was always trained with access to the Z. So the base policy always has the previous state, the state and action, and the Z. Well, at training, regression has tried to ensure that they are the same. Okay. I mean, we can actually do that training with that Z as well. And we have done that. That's what we call adaptive RMA. So that's like a variation on this theme. Okay. And the result is that we finally get one policy which can work in all these conditions. Okay. And but let me give you an example to give an intuition of this idea. So here is a robot which we are going to try to make it walk. So all this research was going on in COVID times. So Ashish was my student. He took the robot home, and this is like his living room. Okay. And he's got this mattress which has got a plastic sheet, and now he's going to pour some olive oil. Okay. And he's not going to just pour some olive oil. He's also going to put some stuff on there is some plastic, socks on the robot's legs. So then this robot is going to, okay, see that? Okay, and now the robot is going to try to walk. Okay, so what did you notice? It was about to slip, right? And then maybe I'll see, you'll see it again in slow-mo. So it's about to slip, and then it recovers. So what should be going on here? So in theory, what should essentially happen is that the Z, which captures the environment, Z is being estimated, and the initial estimate of Z is from hard ground. As soon as it goes onto the slippery surface, the Z estimate is wrong. But it's getting a series of observations of commanded actions and the resulting state, from which it should get re-estimated quickly. And the re-estimation needs to be pretty fast, because it can, I mean, if a human can fall in about 1 second, if you can recover in like 0.1 second, it's fine, right? You can't take 5 seconds to recover. You'll be fallen already. So you need to recover. It doesn't need to happen in 1,000th of a second, but it needs to happen in 0.1 of a second. So the time scales are important. And once you do robotics, you realize that all the time scales have to be considered. Okay, and this is what happens. So our Z is like a 8-dimensional vector. And here are two of the components of the Z. So I think you see Z1 and Z5. And those curves that you see will correspond to the estimates of that in time. So as it is walking, you notice that these two curves at the bottom, those curves correspond to two components of the Z vector, and they are basically changing. And when the Z has changed, that means that we have updated the estimate, and then after that, the policy will do the right thing. Okay, now you've got the big idea. Everything else is like corollaries and a further application. So here's a way to deal with. So here's the robot walking, and then you throw this weight. Okay, the robot's weight is 8 kg, so 5 kg is a pretty significant weight. Okay, so it's having trouble. Okay, but then it will recover. And you can see the recovery in the Z's. You see that the Z estimates are changing, and then after that, its policy changes. So there's a default gate, adaptation, recovered gate. Okay, and now, yeah. We also train with different kinds of masses and so forth. So in some sense, see, what has to happen is that there's a lot of variability in training, but it does not ever correspond to exactly the condition that you'll see in the real world. What you need is that there be proxies for each other. Okay, so this is what happens if you didn't have that adaptation module. Okay, so the top is with that adaptation module, and the bottom is without that, and basically it dies. Okay, and then here is on a soft mattress, another challenging situation. Okay, with RMA it works fine. Without it, okay. And then you can we have done pairful controls to compare against alternative method, because to some extent this estimating the Z is a little bit like systems ID. From a classic control point of view, you'd say you are estimating the system. Okay, it's not. It is like it, but not that, because sys-ID means that you estimate all the parameters of the system. And all the parameters of the system are actually very hard to estimate. Okay, so there is this Vapnik aphorism. When you are solving a hard problem, don't solve an intermediate problem, which is even harder. So sys-ID doesn't work because it's solving too hard a problem. Here, what you're doing is like a projection of the system parameters. Instead of 30 parameters, you're trying to estimate 8. And those are much easier to estimate, and so on. And those are the ones that matter, as you see. And okay, this is one comparison, and those rows show this. Another one is what's very commonly used now, called domain randomization. Domain randomization is that you train one controller which works in all conditions. Okay, that's the idea of robustness. I don't like that. I want adaptive, which is different from robust. Robust means the same thing works all the time. It's going to have low performance. I want to do different things in different conditions. If I know, for that I need to know which condition I'm in, which I capture with the Z. So adaptivity is better than robustness, where robustness in this case has a narrow technical meaning that you have trained one controller, exactly one controller. And this is like the standard technique in the RL and robotics crowd, domain randomization. We believe that our approach with RMA is significantly better. And again, it's borne out by the numbers here. And then you can try to do fine tuning at test time in the real world, and this doesn't work because it takes too much time. So there are approaches which try to adapt in real time for these parameters, and it turns out if you're going to take 5 seconds, you'll have fallen already. It needs to be fast. So that's why we call it rapid motor adaptation. Okay. Now, once you have this, yeah, Rene? Yeah. Yeah. Yeah, so we have done both versions, and when you do them together, it works slightly better. Yeah. So when we first did it, we did it in 2 phases. Then later versions, we did them together, and it works slightly better. Well, it comes down to whether the estimates of Z are really good or not. And if they are really good and ground truth, then it doesn't matter. If they are not perfect, but if you co-learn, then you deal with whatever. I mean, it's a function, and the policy does to deal with it, and it works better. Yeah. So I'm trying to be honest with respect to the paper as we first developed it. Our later papers co-train it. Okay. Okay. Now, then there's the question of how do you, so in the reward function, we specify a velocity at which the robot is trying to walk. So how do you, so you can easily say, okay, let it go at, it should go at 0.5 meters per second, or 1 meter per second, or 0.2 meters per second, right? This is just one parameter in the training, right? And so what happens? And this is what happens. So we train the robot to walk for different target speeds, 0.375 meters per second, 0.9 meters per second, and 1.5 meters per second. And then the following policies emerged. So now you're seeing the policy corresponding to 0.375 meters per second. At the bottom, this RF, LF, RR refers to foot, right foot, left foot, right front, right rear, left rear. And it tells you which foot is on the ground. So what do you see here? What you see is that by just saying go at different speeds, you got different emerging gates. I said philosophically, I did not want to specify the gates. The gates emerge by specifying different target speeds. Okay, so this is great because I think this is more elegant, right? But then you might wonder why this happens, and the answer is already there in the biomechanics literature. And the biomechanics literature, I mean, there's a paper in Nature in 1980s which showed that different gates are more efficient at different speeds. Okay, and basically, so there's an experiment. Sorry, let me go back here. So the one on the right, you see this data for horses. At different speeds, you sort of get these curves of energy consumption. And basically, if you are going at low speeds, It's more energetically efficient to walk. At high speeds, it's more efficient to gallop. Similarly, it's true for humans. At low speeds, we walk, and at high speeds, we run. And it is energetic. We can walk at, I mean, when you see speed walking at the Olympics, people are walking very fast. They do it because that's the rules of the game. But energetically, at that point, you should be running in terms of consumption of energy for meters traveled. Okay. And this just emerges because there's no black magic here. RL is just a strategy for acquiring, training an optimal controller. And the optimal controller, if you get to specify the cost function, and the cost function has energy as a term in it, then appropriate gates will just emerge. Okay, so that's the argument. And then, of course, we have this together with the RMA machinery. So basically, these gates work directly in the real world, not just in the lab. And this is like a demo just to show that it can go really fast. Okay, now I have to ask the question of why do we need vision? Everything so far was blind, and I'm a vision person, and I have to try to prove that why do we need vision? Okay, we need vision because it enables precise locomotion. So if I have these stepping stones, I'm crossing a river and I have to put my feet on this. It's not going to happen without vision. Stairs, I mean, blind people can negotiate stairs, but it's quite difficult and painful. And so here, what's a classical idea? The classical idea is to build terrain maps, right? Because robotics people have got into SLAM. I mean, it's really structure for motion as far as the computer vision goes. It's relabeled SLAM, but and then they apply that to everything. So here the idea would be you have multiple views as you're walking. You have a camera on the robot. You integrate them into a map. That's the obvious thing to do, but it's the wrong thing to do. Why is it the wrong thing to do? Because there is a lot of noise. When you're walking, you're shaking and your camera is shaking. And so the error in the camera estimate means that when you integrate the information to estimate the map, the depth map, that depth map is error prone. And that accumulation of error means that the depth map has so much uncertainty in it that your walking policy then suffers as a result. So what we do is to say, so real world maps accumulate noise. So instead, we'll go directly from vision to control. And we take the same philosophy of RMA, which is that you train in simulation. And the top block, the bottom block is just these privileged information, which estimates Z. But there is another block that we have, which is this M sub T, which is sort of some depth points in the neighborhood of the legs of the robot. So these are called scan dots. And people have used this idea before, just the idea of scan dots, except that they would try to get them from the map. And fine. Okay, so we can train in simulation. Everything can be trained in simulation. And now what we are going to do is that in the real world, we will not have this, right? So you train the robot assuming that you know the depth values in front of the robot, but how are you going to get that? I mean, that's assuming only God knows that, right? So what you're going to have is something different. We have a RGBD camera mounted on the head of the robot, and it's going to have the depth like that. So what you need to do is take that depth and build an estimator for this M sub T, right? Same philosophy. We have some observations from which we built an estimator for Z sub T. Here, it's going to be an estimator for these geometric parameters of the terrain, okay? And so those are called gamma for ground, okay? And but it's the same philosophy, and now you plug that in, okay? And I'm going to go fast because it's okay, but now I'll show you some results of this policy. So now it has a camera on top. There's an RGBD camera. There is nothing, no off-board, everything. On-board camera, on-board compute. Okay. I believe that autonomous robots must be autonomous. Okay. Okay. It has no prior knowledge. It is not building a map. And we have done this experiment with different stepping stools. Okay. So we did 10 times and it fell once. Okay. Okay. And then this is stairs. Yeah, sorry, because it's going through Zoom, therefore there's a lagginess, but it does not know about these particular stairs. We have done this at stairs at Berkeley, Stanford, CMU, in parks. Okay. Okay, this is if someone who's been to Berkeley, there's a rose garden. This is from the Berkeley Rose Garden. This is CMU. And if you look at the height of this robot compared to the height of the stairs, they are actually quite comparable. Okay, which is quite a challenge because Boston Dynamics hardware couldn't, if you scaled it up, it wouldn't be able to climb these kinds of stairs. Okay. Then we did this for bipedal robots. So this is a collaboration with Kaushal Srinath's group. So this is the Cassie robot, which I think is, I feel that in bipedal robotics, really a lot more work needs to be done on the hardware end itself. Quadrupeds, I think the hardware problem is really well solved. Okay. And then there's like the oil slick experiment again. Okay. Okay. So the top is just to prevent this robot from falling and breaking. It's not actually being used. Let me see if there's, okay, so it's now towing something pretty heavy. Anyway, so but it's the same basic idea. Okay, let me okay. Now this idea, by the way, is was for locomotion, but why should it not apply to any other problem? So we tackled this problem of a manipulation. So here we have a multi-fingered hand, which is rotating the object. There is no vision, there is no tactile signal. So only signal is proprioception. And it's exactly the same policy which works for these objects, for all these different objects. And you can see some information about what's the object. The object can have varying shape. It can have varying mass. We have variation from like 20 grams to 200 grams. And then, yeah. So. Okay, so there is this paper towel. Okay, so odd shapes, etc., etc. Okay, but it's the machinery is exactly the same. You train a controller in simulation. You have this adaptation module, which is also trained in simulation. And in this case, I mean, as Rene's question was, if you co-train them, it works better. That's what we did here. And so there's a task reward, and everything is super simple. The reward is just that you try to attain a certain angular velocity, and then the rest of the costs are there. Sometimes there's there's lots of hacks to make this thing work. There's nothing there. It's what you see is what you get. And we train these modules, and then these are adaptation module is being trained, deployed. Okay. And then the gates emerge. So these are called finger gates. And we just, if you have simple objects like spheres, then you get a couple of alternative ways. For more complex objects, what we had was like one gate. But that just emerges. And for these different objects, how is it able to rotate these different objects? It turns out that there are a couple of variables in that z vector, which land up corresponding to scale or mass and so forth. So there's no, that's what happens here. And then I will show you this example. So now this idea also applies to anything, right? So we trained quadcopters. So quadcopters, okay, flying that. Here you can design controllers analytically, right? But your controller for a quadcopter usually is for a specific mass and specific inertia. And here what's being done is that we are attaching a mass to it in real time or attaching something like that, right? But the quadcopter still keeps flying with exactly the same policy. So the idea here is the policy adapts to things like mass and small or big. It's one policy for all quadcopters. And the way we can achieve that is by this estimator for z, essentially capturing that, and then we have a universal policy for different size and different weight quadcopters. One policy to fly them all. And this is a paper which will appear at ICRA. Okay, I'm going to conclude now, and I want to have one last bit of philosophizing, which is that I believe in developmental robotics or developmental AI or whatever. And this is an idea originally from Turing, that we should build a child's intelligence, and then after that do learning. So that instead of trying to produce a program to simulate the adult mind, why not rather try to produce one which simulates the child's and then subject it to a learning program? And there's a lot which is known in the last 30, 40 years, which what Turing didn't know, which our colleagues in child development and in psychology have learned about the behavior of the various stages of development. And I just picked one paper from Smith and Gasser on the development of embodied cognition. There are various aspects like multimodality, incremental, physical, embodiment, explore, etc., etc. So multimodality is that a child explores some object. She sees the object, she touches the object, she puts it into her mouth. So there are many senses which are involved, and now the beauty is that they can cross-supervise each other. So we did an experiment on that, and this is for learning visual locomotion. So the walking that I showed you on stairs before was with an RGBD camera. And now the challenge that I put to Antonio and Ashish, Antonio is a postdoc and Ashish is a student. Ashish is the one who was involved in all the RMA work, was can we get rid of the depth? Because humans should be able to walk with just an RGB camera. And now it turns out that training and simulation is not good enough, because rendering speeds are too slow, and then it will take too much time. So so this is our idea. So let's understand what's the difference between blind walking and visual walking. So this is blind walking. Okay, you'll see this again. Blind people sort of poke around with a stick and then they can walk, but it is slow. I mean, we didn't program this and it just emerged, but it has the behavior of a blind person poking with a stick. Okay. And now we want to make use of vision, but RGB, and we can't train it in simulation. So what we can do is we can train in simulation if you had access to depth, what a policy would be. Okay. And now this is what a vision-based policy is. Okay, you'll see a demo again of the vision-based policy. So you see the difference between blind and vision, right? Okay, let me see if it, okay. The vision is much smoother. So what's the trick? I want to do multimodal learning in the real world when the robot is walking. So it turns out there is a very simple observation. If you consider the robot, so this is the robot and it has all its proprioceptive senses. From its joint angles, it can actually compute the depth of the ground underneath, right? So if you do the inverse kinematic type of calculations, you know that the front feet is above the back feet, right? So the ground underneath the robot, you know the depth, right? Exactly. So that's where this idea comes. So proprioception tells me the depth now. I need vision to tell me the depth 1.5 seconds in the future. So what do? I walk and I collect my proprioceptive signal and the visual signal. Okay. Okay. And now what I do is I train my visual signal. I train an estimator from the visual data to predict the proprioceptive signal 1.5 seconds from now. So the ground truth is there. The proprioception is going to supervise the vision signal, and the vision signal's job is to predict the proprioception 1.5 seconds from now. So that is what you see in this curve. So the visual look ahead target is this, the shifted proprioceptive signal. And now I am going to have my neural network which takes the image and tries to predict that. And now I've got a supervised learning problem. Very easy. Yeah. Condition on the control in the environment. Yeah, it is for the controller. Yeah. So that's it. So now we've got this estimator. And now let's see how this works in practice. So we trained this controller, and the cool part is I'll show you these results. So day one, it's sort of this blind controller, okay? And basically it's the visual estimator is always improving all the time. Okay? And here you actually have numbers for all this. So basically, the third day, we call this the third day, but each day is like 20 minutes of training. Okay. The success rate has gone up, which is in blue, and the CMS error, which is the error between the proprioceptive and the internal training error, has come down. And now my last thing was, like, we got really ambitious. There is this famous prism experiment in motor control, which is that humans, if they are picking up some object, if I put a prism in front of one of your eye, what happens is that all the rays are being deviated by 10 degrees. So you try to reach the object. You can find videos on YouTube. You try to reach the object, but you will be off because you think that the object is there, but basically, I messed with the hand-eye coordination because I messed the calibration between the visual systems, coordinate system, and the hand's coordinate system by putting a prism in front of the eye. You keep doing it, and in 10 minutes, you actually can do it again. Then I can remove the prism, and again, you're messed up, but you'll recover. There's a version of this which is for inverting glasses. It was actually done by a psychology professor at Stanford called Stratton. He learned to bike with inverted world. And then, of course, he had these glasses which were inverting. Then after a while, he removed those glasses, and again he had trouble, but he could readapt. So there is plasticity in the visual motor calibration. So let's see if we can do this. So this is the camera, and Antonio is going to mess with it, okay? Okay, he's rotated the camera. So now this robot's life is messed up, because its hand-eye coordination has been messed up. So it's going to try to walk, but the visual system is giving it the wrong information. Okay, so it struggles, right? But remember, it's always calibrating with vision and proprioception. So let's give it some more time. Okay, and I will show you the. So before adaptation, okay, so that's the painful part. And now this is what happens after adaptation. It's recovered. Because the proprioceptive signal has trained, you get the real world proprioceptive signal and the real world visual signal after actually just 1 minute of data. So my goal is that never in the future will my students have to struggle with calibrating robots and cameras. Okay, calibration should happen all the time, continually. Thank you very much.
Thanks for the great talk. It's always very fun to see how robots struggle and conquer the real world. We'll start with a 20 minutes discussion session. I'll be taking questions from the Zoom session and also from the audience here. I already see it.
Yeah, done.
Hey, Dan, let me get you the mic quick.
Yeah, maybe, yeah, otherwise, yeah, Mike.
Yeah, we've been trying to digest your wonderful, exciting work since Deepak and Ashish talked about came to us about a year ago. I have two seemingly orthogonal questions, but I think they're the same. But the question one is, I grew up in the era when adaptive control, as you had just recovered from the tragedy of the catastrophe of the X-15 that was destroyed, because prior to that, people had used your idea about having time constant separation between the parameter adaptation and the control. That worked very, very well for stable, quasi-stable systems. And then when they put it up on the X-15, it crashed. Anyway, so we spent a lot of time. We were very proud. We had linear and parameters models, and because they were linear parameters, maybe nonlinear in state, we could do adaptive control very, very, very well. I've gone back and forth in my work between sometimes trying the complaint was that there's almost it's a contradiction between robustness and adaptation, because adaptation needs to very, very seriously follow the model. I would have guessed that your solution of very separated timescales would work pretty well until the setting becomes much, much more unstable. But it seems that your adaptation is working just as well in bounds, very, very highly dynamical gates, as well as it does in the more quasi-static setting. Is that wrong? And if it's true that you can do just as well in highly unstable dynamics as in stable, why should the time scale separation work that well? It shouldn't.
It's a fair question, but I don't really have any deep insight to offer. I think that this basically, it would be good to have a theoretical understanding. Right now, I'm just showing you empirically this works well. Okay, but this is the time for theory to take over. There are certain things which experiment can do, and there are certain things which theory is needed for.
So we'll talk. The second question, which appears to be which I think is the same question, is half of the reason for building gates is to get a better understanding as to how to build a better robot, or if you're talking to the biologists, a better understanding about why the animals might be built this way versus that way. Thank goodness you're not a religious end-to-ender by any means. You're a modularity compositional kind of fellow. You yet understand how to critique the design of the robot on the basis of your module or understanding of how things fit together, or is that not yet available to you?
So let's see. So my position on gate is something like this.
Not gate. I mean, you can have feed forward gates, you can have feedback gates. The question is, we use those gate designs, we place ourselves in a feed forward feedback with parametric representations, and we use that to try to critique what the design of the robot was. How far are you from being able to use your modularity to get those kind of design questions?
So design principles on sort of the morphology.
Well, and power distribution and that.
So again, I don't have any answer on that. I feel that, but I think that problem can be studied. So I feel that problem I can approach. The first one, I feel really needs theory in a new way, which isn't quite there. But I hope my control theory colleagues will work on problems like that. But the second problem, I would start with actually just exploration and simulation of different morphologies, and and so on. And then I would try to get some insights. I think, okay, so what, I mean, I saw the work, so let me refer to the work of Karen Adolph again. So, and this is a phenomena found in other biological systems as well. The biological systems of something like let's say the visual system of something like a rabbit, right, or a fly, it has hardwired capabilities very early because it has a relatively small brain and it needs to be functional pretty much after the moment of birth, and it needs to, okay. So for example, there are motion detectors right in the retina of a rabbit. Flies have a very simple hardwired control system between the optical flow and the flapping of the wings and so forth. As you get to these, quote, higher species or more advanced species like humans, where there's a big development stage which is done after birth, okay, what happens is that you hardwire less. What you hardwire is a capability to learn, and then there is a long period of sort of learning and adaptation. That seems to be the solution in nature. So human babies are basically helpless, whereas a horse baby after one day can run, right? So now, why this is so at a deep level, there's a lot of discussion on this. There's an advantage to precociousness and a disadvantage to precociousness. So once you decide, once sort of somehow nature has decided that it's going to take a learning approach, then the trajectory which seems to be followed is that you first learn to walk, then you have a little bit of a stumbling experimentation with lots and lots of falls, and then over time the gait becomes more efficient. Now then the research problem becomes, how does this learning work? How do we deal with this problem of, so basically the learning story with reinforcement learning is not a valid story for child development, because certainly the sample complexity of reinforcement learning is way too high to account for how children learn. They have to be able to learn with far fewer examples. So here I'm a little bit into this, and there's this guy called Nikolai Bernstein whom I'm inspired by. So Bernstein has ideas on how this developmental routine could work. And roughly speaking, those are that initially you don't have so many degrees of freedom. You freeze the degrees of freedom, and now you have a lower dimensional system which is much easier to acquire sort of the basic walking behavior or whatever motor task you're trying to do. And then later on, you unfreeze the degrees of freedom and you make it more smooth, more energetically efficient, etc. So I don't think I have answered your question in an analytic sense, but I tend to be quite motivated by looking at the psychology and neuroscience, and that seems to be the story there. And I hope that we will find sort of an underpinning in mathematical or control theory way of thinking to explain this. Okay. Yeah. Thanks.
Okay, so there are two questions online that are kind of similar. One from Ed that's asked, do you need to be careful in choosing what ground truth system parameters to estimate Z from? I guess it's more related to the first work you presented. Or is it better to just include as much privileged information as possible at training time?
So the answer is use as much privileged information as possible. And because we have this encoder, so the privileged information can be lots of things, right? 20, 30 things, 20, 30 variables. And then it's going through this encoder into, in our case, an 8-dimensional Z vector. And the idea is that this network will figure out what is important, because if the variables which are important will affect the policy, and what doesn't affect the policy doesn't matter. I want to use this to make a point which I think is interesting, which may appeal to you from your physics knowledge. See, in physics, like consider fluid mechanics. We know that there are certain combinations of variables which occur together in a ratio. So Reynolds number, Froude number, if you have studied like Navier-Stokes equations and turbulence, I mean, I had to do this like 50 years ago or 40 years ago, something. And you learn that there are these important parameters which occur in certain combinations, and you cannot estimate them individually, but you can estimate their ratios. So, and this is what enables, for example, airplane designers to do experiments in a wind tunnel, which is not exactly the same situation as in the real world. But if the Reynolds number is matched, you're going to get similar behavior in fluid flow. Now, what that means is that actually the original 30 variables are not important. Certain combinations of them are important. So that we know from the physics and fluid flow. So similar things will happen here. Certain combinations will matter, not the raw variables. So when you do systems ID, which is what classical control theory people would do, they're doing the wrong thing. They're trying to solve for those individual variables, which may be not estimable and they don't even matter. The ratios matter. I'll give an example from computer vision. From optical flow, you cannot estimate the distance to an object, nor can you estimate the speed of an object. You can estimate the ratio, which is what matters because that's the time to collision. So all of this kind of stuff, which we in computer vision have known, I think that kind of thinking needs to go through in motor control as well. And I think this Z in a somewhat hackish way is capturing that idea.
So this kind of partial identification of system parameters that's happening in the adaptation module is relying on recent history of states and actions induced by your policy over the last few time steps, right?
Yeah.
And the policy appears to have been trained mainly for solving the task. It's not even aware that partially its outputs are being used to adapt, right?
Yeah.
So does this lead to situations where the adaptation module is unable to extract the information necessary from just this time window? Would it make sense to have some kind of explicit incentive for the policy to generate information?
Yeah, so I think that the first version that we had just did it separately, and it is susceptible to some problems unless the estimation of these Z's is easy enough. Okay, and basically in later versions, I think this is Rene's question. In later versions, we trained them together. So then essentially, if the Z estimator is not perfect, the policy learns to deal with it because it's getting that as the input. So that's probably the right way to do it. We just historically did it one way, and I didn't want to cheat because I'm talking about that paper. I couldn't forward correct it, you know.
Yeah, kind of similar question, kind of quite close to that is, so you mentioned kind of at the beginning of the talk that it's, there are two ways of viewing what you're doing. You're either identifying portions of the state that are unobserved or parameters of the model that are unobserved, right? And if you think of the portions of the state view, then there is a literature on POM-DPs and how you deal with POM-DPs, perhaps in reinforcement learning by using histories and windowed histories as input to the policy and so on, right? So those kinds of approaches, do they fail mainly on account of not doing this kind of temporal separation, the time scale?
No, so I'm not a fan of POM-DPs. I think it's like a computer scientist way of making things complicated. Okay, it's basically it's like taking a hard problem and making it much harder, right? Because now you have a probability distribution over all these things you don't know, and complexity is just intractable. And yet every damn animal can walk, right? So therefore, there must be a simpler way to think about it. So I essentially just feel that POM-DPs have basically taken the things that they couldn't estimate and then putting a distribution on them made the problem much more difficult. Whereas what I'm saying is, I don't need to estimate all those variables. I just need to estimate a projection of them. And I can estimate, and the ones which matter are the ones which affect my actions. So So it's so I like yeah I mean there's a huge literature on POMDPs. I mean one of my colleagues, Stuart Russell, is very much into this. These are the kinds of things which you can write down, but I think they're not tractable. They're tractable for very, very simple systems. So it's a very computer science way of thinking it. You can say, yes, in theory, I've got a very clean formulation, but it's not, I think, except for very toy problems, it'll never be tractable. Whereas the control theory way of thinking is that, okay, you're capturing the state in some Rn, Rm. To me, that's the right way. So capturing the parts which of the environment also has some kind of Rn, Rm, you know, some real, I think that's a better way than, I think, anyway.
All right. So that was a lot of.
We had one more question up here if we still have
one
time.
more idea. Okay.
Yeah.
Hi, so I wanted to ask about the role of simulation in robot learning. So I think a theme that goes underneath a lot of the works you presented is like how much we can do from using simulation. I previously have thought, you know, simulation should help you to get an initial policy and you do the adaptation in the real world, but you have shown that you can even do like learn how to adapt in simulation. So I wonder for tasks or domains where high quality simulation is hard to get, what would you suggest doing in those situations where you think, okay, the route forward, the path forward is just developing better and better simulations so you can do everything in simulation using RL because, you know, you can get a lot of samples very fast.
So the answer is both. So I think that there needs to be adaptation in simulation and there needs to be real world adaptation. So the last part of my talk, I showed adaptation in the real world. I think all the systems we build should always be adapting in the real world. So adaptation is not something that happens just once, okay? Adaptation, so I think that this is true for the critique of the classical approaches too. The classical approaches, like where you design your controllers, if they are not adapting in the real world all the time, then there's something wrong with that. So I'll give you an example. I'm walking, right? Okay, suppose I sprain my ankle. Okay, so does my system collapse? No, I walk with a little hobble. My gait changes a little bit, but I can walk. All the time we are adapting all the time. So that has to be done in the real world. There's no choice to that. With respect to the simulator, the thing which 5 years ago, I would have said, I hate simulators. This stuff will never work in the real world. But I've changed my mind. I first worked on navigation problems and we found we could translate them to the real world. Then I thought contact problems will be hard and those won't be, well, walking requires contact and we could do it. I think there's still complexity with like dealing with friction and contact and so forth, but they're getting better all the time. And companies like NVIDIA have invested in a big way. So my general belief is that the technology of simulation, because it also benefits from Moore's law and computing advances, it's getting better all the time. And so we should exploit it to the maximum, okay? And when you have a complex system, what do? Right? A classical control theorist would say, let me write down some equations and then solve them analytically. Those equations are approximations, okay? And those approximations can become quite terrible. So I think that's not, I think a better future is to do simulation because that's also got approximations, but they may be better, there are approximations because the computer can deal with more complexity than me as a mathematician. So I feel that the approximations inside a simulator are less severe than the ones when you write down the equations, right? Okay, so that's my argument for using simulation. But my argument is not that okay, that's where all the adaptation gets done. No, adaptation is a lifelong thing. It has to be done always, all machines. So my realization is every robot and camera system should always be adapting all the time.
All right. So with that, I think it's a good time to thanks Jitendra for this very inspiring talk. I hope all of you enjoyed it. Yeah. Thanks, Jitendra.
Thank you.
Closing remarks is please tune in for next Friday, March 3rd, 10:30, and the talk will be given Jeanette Brown from Stanford University. So we're in a treat again for next week.